everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be looking at some of the most common misconceptions around hypothesis testing, confidence intervals, and p-values. We're following Bess. She's an investigative journalist on a cold case she can't let go. Today she's looking at how a bank's internal risk team used statistical language to justify a major model rollout. The question she's trying to answer is whether the statistics actually supported the claim. The bank developed a new loan approval method that was designed to reduce defaults on its loans. When they ran a pilot test of this, the pilot produced a p-value of 0.03 when compared to their old model. So senior management approved the full rollout. Bess pulls up her case file to figure out what's really going on. The bank's internal report made a specific claim. The p equals 0.03 confirms that Model B reduces defaults. There is only a 3% chance that this result is due to chance. That sentence contains two mistakes, and they're the kind of mistakes that show up constantly in practice. You end up seeing them in research reports, in pitch decks, and regulatory findings. So before we go any further, it's worth getting very precise about what the p-value actually says and what it does not. We covered the definition of a p-value in the previous video, but it's worth restating it carefully here before we get into the misconceptions. A p-value is the probability of observing a test statistic as extreme as the one that you got, or more extreme, assuming the null hypothesis is true. The first misconception is the most common. It goes something like this. P equals 0.03 means that there's a 3% chance this result is due to chance. That is not what a p-value is. A p-value is a conditional probability. It is conditioned on the null actually being true. It tells you how surprising the data would be if nothing were going on. It does not tell you the probability that nothing is going on. Treating those two things as the same is a fundamental flaw in logic. So how exactly would we correct this statement? Well, our p equals 0.03 tells us that there would be a 3% chance if the null hypothesis was true that we would generate a result at least this extreme. The difference there is that we're conditioning on the null hypothesis being true, but in the real world we don't necessarily know whether that's the case. So we can't make blanket statements about what the probability is that this was due to chance. The second misconception is that p less than 0.05 proves the alternative hypothesis. It does not. Rejecting the null hypothesis gives you grounds to conclude the null is not consistent with your data. It does not prove that the alternative is true. It does not prove that Model B works. It says that the observed difference is large enough that it would be unusual to see it by chance alone. That is a much narrower statement than this model is proven to reduce defaults. The third misconception runs in the other direction. If the pilot program had returned a p of say 0.15, some analysts would write that there is no statistically significant difference between the models, confirming that they perform equally. That is also wrong. Failing to reject the null does not prove that the null is true. It might just mean that the pilot was too small to detect the real difference. We covered this directly when we talked about statistical power. A null result from a low-power test is nearly uninformative. The fourth misconception is the one that gets the least attention but is just as important in practice. Statistical significance is not the same as practical significance. A sufficiently large sample will make almost any difference detectable. You end up with statistical significance on effects that are too small to act on. So if the bank had run this pilot on 100,000 applicants instead of a few hundred, a difference of, say, 0.01 percentage points might have cleared our boundary of p less than 0.05. But that does not mean that the 0.01 percentage point reduction is actually worth anything. In fact, the two models basically perform the exact same in terms of the actual significance of what they end up achieving. So sure, Model B might be statistically better than Model A, but is the economic difference between the two worth completely overhauling the bank's entire underwriting system? Probably not. So keeping these two things straight within your mind is important when making decisions. This is exactly where confidence intervals become the better tool. The 95% confidence interval for the reduction in the default rate in a bank's pilot program turned out to be from 0.2 percentage points up to 2.8 percentage points. That interval excludes 0, which is why the test came back significant at the 5% level. A two-tailed hypothesis test at alpha equals 0.05 and 95% confidence interval are two ways of answering the same question. If the null value falls outside the interval, then you reject. If it falls inside, you don't. They are mathematically equivalent on a standard two-tailed test. But the confidence interval tells you something that the p-value never could. The p-value says that the reduction is real, and the confidence interval says the reduction is real, and it probably falls somewhere between 0.2 and 2.8 percentage points. At the lower end of that range, You're talking about 2 extra defaults prevented for every 1,000 loans. Whether that justifies a full system rollout is a business question. The p-value doesn't answer it. The interval at least lets you talk about it. That is why analysts who report responsibly show both. The p-value gives the significance decision, and the confidence interval gives the effect size range. Together, they tell a complete story. Separately, the p-value gives you only half. In Bess's case, the bank's risk team reported only the p-value. They did not report the interval. A regulator reviewing the rollout decision later flagged exactly that gap. In her article, Bess explains this to her readers. The test said that the new model was better. What it didn't say was by how much. And in credit risk, how much is the whole question. So that's the misconceptions around p-values and the connection to confidence intervals. A p-value is a conditional probability. It assumes the null is true and asks how surprising the data would be in that circumstance. It does not tell you the probability that the null is true. Rejecting the null is not the same as proving the alternative. Failing to reject is not the same as proving the null. Statistical significance and practical significance are 2 different things, and a confidence interval is the tool that bridges that gap. Report both and you've told the full story, but report only the p-value and you've told the easier half.